Good morning, everybody. I'm Giacomo Ibba, PhD student of the Department of Mathematics and Computer Science at the University of Cagliari. The work that I'm presenting to you today was carried out with the help of Antonio Pierro and Marco Di Francesco, and it concerns evaluating machine learning techniques and in particular text classification techniques for detecting Ponzi scheme constructs inside the Ethereum blockchain. In particular, our presentation provides a brief introduction in which we'll see the basic definition of our work, helping understanding what we are talking about. Then we see how it's possible to define a Ponzi scheme contracts using the Solidity programming language, and then we see the research questions that brought us to carry out this work. After that, we'll see in details our research methodology. In particular, we see how we collect our dataset of contracts, and then we see the models we choose for our classification task and their evaluation. Finally, we'll see the results of our classification and relative conclusions and future work. The first definition I want to give to you is the definition of smart contracts. Smart contracts are general-purpose programs that allow the execution of secure transactions without the help of third parties. The goal of smart contracts is to provide a higher level of security than that offered by traditional contracts and reduce other transaction costs associated with the bargaining practice. The goal of smart contracts is to provide a higher level of security than that offered by traditional contracts and reduce other transaction costs associated with the bargaining practice. Everything directly stored inside the blockchain is public, so anyone can read everything is directly stored inside the chain. In the context of smart contracts, if the source code is available, then anyone can read it. Since we are in the Ethereum context, it's useful to define a malicious user and its behavior. A malicious user is a network participant that tries to convince other participants to invest their money in high-risk contracts in which there's no guarantee of getting back their ethers. Obviously, these kind of contracts are considered fraudulent contracts, and to develop these kind of programs, a malicious user wants to exploit the inner properties and advantages of the blockchain. One of these advantages is the anonymity, because a participant can stay anonymous inside the network. Trustworthiness, because previously we said that as if a smart contract is stored inside the blockchain and the source code is available, then anyone can read the source code of the contract, and we can say that an investor is more inclined to invest his money in something he can read and he can try to understand, respect to something he cannot read and he cannot try to understand. Another possible advantage is the possibility of programming immutable and potentially unstoppable contracts, because we must remember that the blockchain is an append-only structure, and so anything directly stored inside the chain is not deletable. In particular, we are interested in a type of fraud that is the one of the Ponzi scheme, and is a pyramidal scheme in which investors are recruited with the promise of easy earnings and high interest rates relative to the initial investments. What's interesting is that the scheme participant can recruit new investors to increase their earnings, and this is particularly interesting in the Ethereum context because in Ponzi scheme contracts, a participant, to get back his money, must recruit a new investor and it must make it join the scheme. So this is a necessary condition. We refer to smart contracts that implement a Ponzi schemes as smart Ponzi, and these smart Ponzi contracts have a common structure and a common cyclic flow. They have some general rules, and the first rule is that a minimum investment is required to join the scheme. Investors start to get paid only if funds are sufficient. The third one is that if new investors are not available anymore, the scheme is broken. And finally, if funds are not sufficient to pay the investors, the scheme is broken as well. Well, other than this, there are some other common features to the Ponzi scheme contracts, and these features are, for example, that a smart Ponzi is defined by a contract owner and by participants that are defined by their addresses and their balances, and all the participants are stored inside a data structure, and this data structure could be a mapping or an array. It depends on the type of contract, and every smart Ponzi contract has two functions. One function takes care of the participant's payment, and the other function allows a new participant to join the scheme. The research questions that brought us to carry out our work are the following. Is it possible to classify smart Ponzi taking advantage of natural language processing techniques? We'll see in just a moment why we want to use these kind of techniques. Have all smart Ponzi contracts been developed for malicious purposes? I anticipate to you that some of the Ponzi scheme contracts are very similar between them, and few of them are copies of other contracts. So this should give you an hint about the answer of this question. The third one is possible to build a classification model able to classify any type of fraudulent contract? Before answering this question, I present to you our research methodology. We started from the addresses of contracts, and then we scraped all the text, our text feature from etherscan.io. Why text feature? Well, because we said previously that the smart Ponzi contracts have a common structure. So the main idea is that their opcode will be similar as well, and there are a lot of terms that help to identify the contract only by reading the source code. These terms are pyramid, head of the pyramid, investment, payout, recruitment, scheme, join, and other terms like this. So what we did was to scrape the source code for all of our contracts, and we were very lucky with that because the source code was available for all of our contracts, the opcode, the ABI, and transaction information. After scraping our text feature, we computed all the abstract syntax trees for all of our contracts, and they are very useful to get structural and semantic information from contracts. For semantic information, I mean variable names, function names, conditions inside the for, if, while constructs, and function names. So what we did was to extract these semantic features, and then we built, tested, and evaluated our models. But before presenting to you our models, I want to go deeper inside the semantic extraction process because I understand that it's not a so trivial process and it could be a little tricky to understand. But let's see an example. Suppose we have the following Solidity expression. If message.value less 50 penny. Well, this is what is called if statement inside the abstract syntax tree. And what we did was to decompose this expression to have single pieces of expressions. For example, message, value, the symbol less, and 50 penny. So after going deeper inside the ASP and decomposing our expression, our parser will return a sentence starting from the expression. For example, the expression if message.value less 50 penny is returned as a sentence, that is, if value of message is less than 50 penny. The first model we decided to use is the decision tree model, which is one of the simplest classifier and is useful for both the classification and regression problems. As the name suggests, it works by representing tree structure structuring from data, and the only problem with this model is that it is inadequate to predict continuous values and very long average time to train the model. But we are not going to predict continuous values, and let's say that we don't care about average time of training. The second model is the support vector machine model that maps training example to Point space. And it's a memory efficient model, and it works pretty well when the two classes are linearly separated. The only problem with this model is that it's not known to work well with large data sets. The last model is the Multinomial Naive Bayes model that belongs to the Bayesian classifiers family, and it considers a feature vector where a given term represents the number of times it appears or the frequency. The best thing about this model are that it has a low computational cost, it can work with large dataset, and is well known to perform well in text classification problems. So this last point makes it a perfect choice for our classification task. Now we present our classification methodology. What we did was to build two different datasets, one with source code and transactions as text feature, and the other with source code and opcode as text feature. What we want to do is to test all of our three models with the two different datasets with different parameters. We'll see in a moment what these parameters are. What we did was to evaluate the model with class metric evaluation like precision, recall, F1 score, and accuracy. And we chose a cross-validation approach. And what we did was to drop all the empty fields and possible duplicates from text. And then we converted our collection of documents to a matrix of token counts. Then what we did was to perform data normalization and any other character normalization, and we remove all the words that commonly appear in the English language. Now I present to you the results of our models and the accuracy reached by our models. The first table we see is the decision tree table, and we see that it was able to reach high accuracy. It was able to reach an accuracy of 98% with source code transaction as text feature. The criterion parameter allow to choose between the Gini impurity and the information gain based entropy to measure the quality of a split. We see that there's not much difference in choosing the Gini impurity or the entropy. Indeed, the source code opcode feature with Gini return 97% accuracy, and the source code opcode entropy return 0.98%. But there's no difference in choosing Gini or entropy with source code and transactions as feature. The only difference is that the Gini impurity allow us to not compute logarithmic functions, which are pretty expensive in terms of training time, and so it's better to use the Gini impurity if we care about the training time. The second table is the multinomial naive Bayes table, and I anticipate to you that it was the best model in terms of accuracy. Indeed, we were able to reach an accuracy of 99% with source code transactions as text feature. The fit prior parameter allowed to choose whether to learn the prior probability of a class or not, but just looking at results, we see that there's no difference in choosing to learn priorly the class probability. So it was the best model, and the source code transaction as feature allowed to return a better accuracy. Indeed, we were able to reach a 99% accuracy with the source code transaction as text feature, and 97% accuracy with source code opcode as text feature. The last table is the SVM table, and it was able to reach better results than respect to the decision tree and worse results respect to the multinomial naive Bayes model. Indeed, we were able to reach a 98% accuracy in all of our different cases. Indeed, we were able to reach 80% with source code and opcode as text feature, and 80% with source code and transactions as text feature. The loss parameter allows us to choose between the Inga and squared Inga loss function. So, just looking at the results, what we are able to say, we are able to say that the best results were reached by the multinomial naive Bayes model, and obviously we are able to answer to the first of our research question. It is possible to classify smart Ponzi schemes by taking advantage of text classification techniques. But I want to go deeper inside the high accuracy we were able to reach. I want to say that we were able to reach such high accuracy because the Ponzi scheme contracts are very, very similar between them, and some of them are copies of other contracts. So the structure is pretty much the same, and a lot of contracts were kind of the same in terms of operations and also with the name of the variables. So the problem is that our most recent smart Ponzi contracts is dated by 2019, but the Solidity programming language and the Ethereum blockchain are continuously evolving. So therefore, many new strategies of building smart Ponzi contracts may arise, and an approach like this could not work in future. So what we want to do is to improve this model and use not only text classification techniques, but other kind of techniques to improve the model and make it classify any type of fraudulent contract. But this type of the type of techniques must be studied, and so we leave it as feature work. My presentation is over. Thank you for your attention. Able to reach